All right, this is exam 1 for physics 202. First, the magnitude of the charge on an electron is approximately what? Well, the charge on an electron is 1 or negative 1 times the fundamental unit of charge. That's negative 1.6 times 10 to the minus 19 coulombs. So the closest there is C. It's the approximate charge or the magnitude of the charge. When you charge an object by deduction, well, you don't touch the object because induction means you don't touch it. You bring a charged object near, but do not touch the ball. That is the correct answer. You do not induct the ball. That doesn't really make sense. And you don't move electrons from your finger to the ball. So B is the right answer there. An electrical insulator is a material, which of these? Let's see, through which electrons do not flow easily. It's just the definition of an insulator. I have these two pairs of charged plastic cubes. Cubes 1 and 2 attract each other, and 1 and 3 repel each other. So let's say that number 1 was positive. That would mean that number 2 would be negative. And if number 1 is positive, that means number 3 is positive. And how about 2 and 3? So that's going to be a negative and a positive. They will attract. That is C for number 4. For 5, I have 2 uncharged metal spheres brought into contact. A positive charge rod is brought close to L but not touching, as shown, and then they're slightly separated and the rod is withdrawn. All right, so I have this positive charge here. That's going to set up a negative charge on this one and a positive charge on that one. And then when you separate them and take away the rod, they're going to keep that charge. So L is negative, M is positive. B. Consider this arrangement of charges. What are the which are on the vertices of an equilateral triangle? Which of theirs best represents the direction of the net force? All right, on this 4Q charge, I have 2 forces. I have the force due to this charge, which is going to be attractive in this direction. And then I have the force due to this charge, which is going to be bigger because that's a bigger charge by 50%. So it'll look like that. And so it's neither A nor D because it's the sum of these two vectors. It's going to have to be C because the resultant of those two vectors, or the sum of those two vectors, is going to be closer to the bigger vector. So it'll be right there. Let's see. Number 6. Number 7. Where is the electric field 0? All right, let's look. So let's consider this charge, or a point right here, rather. The electric field due to this charge, a positive charge, is going to be in that direction. And then the electric field due to this charge is also going to be in this direction. It's going to be big. Now, so obviously it can't be 2. So that gets rid of those. Now let's look over here. The electric field due to this charge is going to be in this direction. And then the electric field due to this charge will be in that direction, but it's going to be smaller because, see, I'm further away from a smaller charge. So the electric field due there is going to be a lot smaller than the electric field due to the negative 4 coulomb charge. Now let's look over here, and this is going to be the answer. Also, 3 is not an answer, so that gets rid of that, and that just leaves A. The electric field due to the positive charge is in that direction. Right? And then the electric field due to the negative charge, this charge, now I'm further away from that bigger charge, and so my electric field is smaller. And so there is a point where these two are equal, and they cancel one another out. All right, which of these statements is true? Both charges are negative. That's not true because they have to be positive because the field lines are coming out. Charge A is positive, charge B is negative. Both charges are positive, so either C or D. But if you count the number of lines, they both have equal number of lines, so the magnitude of the charge is the same. Where is the potential equal to 0? Well, let's just look at each point. Here, the potential is not 0 because the distances between those 2 points, the negative and positive 2 coulomb charge, are different, and so the potentials of those don't cancel out. Remember, if I have a +2 and a -2 coulomb charge, for example, if I have a point that's equidistant to them, the potentials are going to cancel out. Because the distances are the same, and so since I have a positive charge here and a negative charge here, my net potential equals 0. All right, but that's not the case over here. All right, so it can't be point A. Point B, let's see, I'm that distance from there to there. All right, those potentials cancel out. There to there, those potentials cancel out. And there and there. All right, those potentials do cancel out. Now let's just look at the others. So that was, what was that, B? So B is the right answer. But let's just look at C as well. Those are different distances, so those potentials don't cancel out. Likewise, the 2 coulomb charges don't cancel out. Here, I'm a different distance from there and there, so those potentials don't cancel out. And similarly there, those are different distances. So B is the right answer. All right, which of these is a conservative force? Field forces are conservative. That is 1 and 3. Charged particles, it's an electric field as shown here. If the particle follows the path shown by the dashed line, that is upwards, how much work is done to move the particle. Okay, well, the electric force, let's assume that it's positive. The electric force, Fe, is in that direction. All right. So that means that you don't have to do any work moving in this direction because there's no work required to move along that direction. You can also think about this. This is an equal potential line. And to move along an equal potential line results in no change in energy, and so no work is required to be done. So that is A. Consider this charge. The arrows represent field lines. The dashed lines represent equal potential lines. What is the sign of the charge? All right, field lines are coming out, so it's positive. For the previous question, where is the electric potential the least? All right, the electric potential is the least. Remember, V is KQ over R. When R is big, V is small. So it's the least at the largest points. That's going to be point A and point D because they lie upon an equal potential line. So D is the right answer. Units of electric potential, the volt is dimensionally equivalent to what? Okay, remember potential at its very basic level is just energy per charge. And so if we just plug in our SI units, that's going to be joules per coulomb. That is A. An electron is released at point A in potential described in this figure. What direction does it travel? Okay. Remember our little figure here of our electric plates. I have a positive, this is my high potential side, and my negative side is my low potential side. If I let an electron go in there, it's going to move in this direction. So electrons move from low to high potential. So here, it's going to move from low to high, so it's going to move in this direction. So that is A to the left. All right, let's look at this. What is the magnitude and the direction of the electric field at the point labeled P? All right, so first of all, let's draw our vector. So I want to know what is the force. I'm going to call these, give these some particular names. I'll call them Q1 down here, Q2, and Q3. Let's get a slightly different color. So the electric field due to Q1 at this point is going to be down. That's not any better, is it? Is going to be down. So I'm going to call this E1. The electric field due to Q3 over here is going to be in this direction. I'm going to call that E3. And then the electric field due to Q2 will be right here, and I'll call this E2. Okay, now I also need to know this angle right here. I'll call it theta, and I need to know this distance. But notice this is a 3 meters here, 4 meters here, so this is 5 meters. That is, I just use the Pythagorean theorem, 3 squared plus 4 squared equals 5. And then I can also find theta is the inverse tan of 3 over 4. Which is equal to 37 degrees. So I have 37 degrees here, and this is also 37 degrees. Now if I draw my coordinates, they look like that. Let's redraw that over here. Actually, no, I'm going to go ahead and calculate what is E1, E2, and E3. So E1, KQ over R squared, Q, for E1, we're looking at 2 nanocoulombs divided by R squared. So this is divided by R1. That's going to be this distance. So that's 3 squared. And that's going to cancel out there, and there, there, and there. And I'm left with 2 newtons for E, or 2 newtons per coulomb for E1. Now E2. KQ2 over R squared. What was Q2 is 1 nanocoulomb divided by the distance, which is 5 squared. And that's equal to 0.36 newtons per coulomb. And finally, E3, K, Q3, which was 3 nanocoulombs, divided by the distance squared, which is 4 squared, and that's 1.69. All right, so those are my magnitudes of my electric fields. Let's just redraw this, and then we'll do the vectors. I have 0.36. So let me draw E1 first. E1 had a magnitude of 2. I had E2 had a magnitude of 0.36. And then I had E3 had a magnitude of 1.7, and this angle is 37 degrees. Let's double check that. E2 is 0.36, E1 is 2. Yeah, that's right. Okay, so now I'm going to take this, and I want to find the components of this vector. And so I say 0.36 cosine of 37. And 0.36 sine of 37. That finds me my x and y components of E2. And let's see, I get 0.22 for the y component and 0.29 for the x component. Okay, now I can just redraw this again. I have 1.7. I have 0.29. This is my x component of E2. 0.22 and 2. Now, I combine these like components. I add these together. I take the difference of these. And on my new coordinate system, which I'll just draw right here, almost done now, I'm going to get 1.8. That's the difference of 2 and 0.22, and 2. Okay, that means that my resultant vector is going to be right there, and I want to find out what that angle is. And so now to find the magnitude of that vector, say the square root of 2 squared plus 1.8 squared, and that magnitude is equal to 2.7 newton per coulomb. So that's the magnitude. And then I want to find phi. C inverse tan of the opposite over adjacent, that's 1.8 over 2, which is 42 degrees. And then I was looking also for the qualifier that's 42 degrees below the negative x-axis, but you could have listed it also from the positive x-axis. All right, particle force to mass is 10 grams and the charge is 2 coulombs. Is in a potential field described by this function. All right, so I got this function. I want to know the electric field. And remember, the electric field in a particular direction is the negative of the partial of the potential function with respect to that direction. So we only have x and y components here. So let's find our x component, Ex, is going to be negative del del x. That's just the derivative with respect to the x of 3y cubed x minus 4xy. Now when you take this derivative, you just treat whatever you're not doing the derivative with respect to, in this case y, you treat your y's as constant values, so you just treat them like numbers. So the derivative of 3y cubed x is just going to be 3y cubed, remembering this negative right here, and minus 4y. Let's just go and put our value here. We have x equal 1, y equal 1, so that's going to be 3 minus 4, so it's a negative, negative 1, or positive 1. That's in the I direction. Now, EY, very similar. Let's see, it's going to be negative 9y squared x minus 4x. And then you put in x equal 1, y equal 1, and you get negative 9 minus 4, which is negative 5 newtons per coulomb in the j direction. So now I have my electric field in vector notation. I think that was the first part, right? Yeah, so E is equal to 1I minus 5J newtons per coulomb or volts per meter. That's the first part, part A, that was worth 6 points. And then for part B, I wanted to know what is the initial acceleration, or what is the magnitude of the initial acceleration of this particle. So I have a couple of information. I know that it's 10 grams and the charge is 2 coulombs. So the mass is 10 grams and the charge of this mass is 2 coulombs. 10 grams is 0.01 kilograms. Move it over 3 places, the decimal place, and that gives my mass. I have the electric field, but I want to know the magnitude, so I'm going to figure out what is the magnitude of that electric field. That's going to be 1 squared plus 5 squared, the square root of that, and I get 5.1. And, okay, so now we want to know the acceleration, but I know that F is equal to QE. I also know from Newton's second law that F equals ma. So I can equate these two and get QE equals ma. So A equals QE over m. 2 coulombs, 5.1 newtons per coulomb. Notice my coulombs cancel. Divided by the mass, which was 0.01. Rounding off, that was in kilograms, I get 1,000 meters per second squared. And that was the correct answer for part B. That was worth 4 points. When I consider this configuration of charges, how much work is required to assemble them in this way? You could have done this a couple different ways. I'm going to do it with this idea of potential energy. That is, the potential energy of any two charges is equal to KQQ over R squared. Or excuse me, not R squared, R. Oh, let me get that out of there. Oh, yeah. So we have 3 sets of pairs here. We have this set of charges. There's a potential energy associated with that set of charges. There's also a potential energy associated with that set of charges. And there's potential energy associated with that set of charges. I'll call this set number 1. I'll call this set number 2, and I'll call this set number 3. And now I just want to calculate that potential energy for each set and add them all up. So the potential energy of set number 1 is going to be 9 times 10 to the 9th times 3 nanocoulombs and 1 nanocoulomb. Divided by the distance, which is 3 meters. So that cancels there and there, that cancels there and there, and I get 9 times 10 to the 9th. Negative 9th, excuse me. So that's PE1, PE2, K, QQ over R. These are the two charges that we're considering. I have 1 times 10 to the minus 9 coulombs. And then I have to include this charge, but don't forget the negative. So that's 2, negative 2 times 10 to the minus 9. Divided by the distance, which is 4 meters. And that gives me the energy for set number 2, which is negative 4.5 times 10 to the minus 9 joules. And then finally we do PE3. Not forgetting the negative. Divided by the distance, which was 5 meters on the hypotenuse of that 3, 4, 5 triangle. I get negative 10.8 times 10 to the minus 9 joules. And then I just add those up. And when you add them all up, the sum of those 3 numbers is negative 6.3 times 10 to the minus 9 joules, and then that was the correct answer. All these questions were basically a homework problem. So remember, the homework is always a good place to practice for the exam. They're pretty basic questions, actually, but y'all did well on it. So all right, here, so I want to consider this configuration of charges. What is the potential at point P? All right, so to find the potential of a collection of charges, I just add up the potentials of the individual charges. So V1 plus V2 plus V3, add those all up. I'll need to know this distance, but we've had this triangle before, so I know that distance is 5 meters. It's a special 3, 4, 5 triangle. And then V1, I'll call this Q1, Q2, and Q3. So V1 is going to be KQ over R. V is equal to KQ over R. So it's 9 times 10 to the 9th. Q for Q1 is negative 2 times 10 to the minus 9. Notice I carry the sign there, and I convert the charge to SI units divided by the distance here, right here, which is 3 meters. So that cancels with that, gives me a 3. That goes away, and I get negative 6 volts. All right, so V2, similarly, that's this charge right here, divided by 5. That cancels, gives me 9/5 volts. This is what, 1.8 or whatever. And then V3 is this is 6 3/4, 6.75 volts. Then just add those up. The total voltage is the sum of those 3 numbers, which is 2.6 volts. That's the answer. And then I want to know how much work is required to bring a negative 2 coulomb charge from an infinite distance away and place it, take it from very far away and place it right here. I know in general that the work is equal to Q times delta V. I'm taking a 2 coulomb charge. Oh wait, no, was it a negative 2 coulomb charge? Yes, I'm taking a negative 2 coulomb charge and giving it a change in potential of 2.6 volts. Because when it's at an infinite distance away, it experiences 0 potential from those other charges because R goes to infinity. But as you move it closer to those charges, it sees a change in potential, and that change in potential is equal to 2.6 volts. And so the amount of work to move it there is negative 5.2 joules. That's the answer for part B, which was worth 4 points, roughly. All right, number 23. Consider this dipole, label the electric field and equal potential lines. All right, so first of all, field lines go from positive to negative. And then y'all did this in lab, though if you weren't in lab, I was very lenient on this, though we did do this in class. It looks like this. You can imagine at any one of these points that if you have a positive test charge, they're going to feel a force that is tangent to the field lines. So if I have a force right here, a positive test charge there, it's going to feel a force in that direction. Over here, it's going to feel a force in that direction. Draw a few more. How many is that? 5. Let's draw more. And then to draw our equipotential lines, we just draw lines perpendicular to the field lines at all points. Sort of looks like a basketball court. All right, as I said, if you were in lab, you did this ad nauseum. If you weren't in lab, most of you got it right, actually. I think practically everybody did. All right, if you weren't in lab, I was very lenient. Okay, I think that's all. There's the multiple choice answers, and you can find this online.